Okay, so let's jump in. So the work that I've done in my lab in my career to date has largely been under the umbrella of idiographic science. And this approach where we try to do quantitative empirical research, and certainly we're interested in group findings, we're interested in generalizable understanding, but we start from the level of the individual. Why do we do that? We do this to avoid aggregating individuals, and we do that because of this idea that we might assume that individual people are not inherently exchangeable. So when we're doing any kind of data analysis in traditional linear models, say, we have to aggregate across our rows to generate statistical power to be able to estimate means and standard deviations and variances and covariances. And in traditional approaches, those rows are individuals, and we average across those individuals in order to derive means and variances and covariances at what we call the between subject level, right? Um, what we don't always acknowledge, although I've written about it quite a bit, of course, Peter Molinar, many other people, is that we're making the assumption that those rows that we're averaging across, that those are exchangeable, right? That we can trade any given row for any other given row. And when you really start to think about the fact that those rows are individual people, we might think that that's a bit problematic. Um, but when we switch to an idiographic approach, we run into a different problem because now we are assuming that the rows in an idiographic data set, which are moments in time, are also exchangeable. And we might question whether that's a good assumption. I think that there's plenty of times when it is. And in fact, going back a point, I think there's plenty of times when it's a perfectly reasonable assumption that we can look at between subject effects. Um, there's lots of questions that are between subjects that require between subjects approaches, and that's not only appropriate, it's called for. So there's times when it's appropriate between subjects. There's times when it's appropriate within a subject. But again, I think there are also occasions or circumstances where we might question whether it's a good approach to average across time points because we might wonder whether those time points are exchangeable. So then the question becomes, is it possible? How can we try to locate individual moments of time in individual people? And for me, the motivation here, well, there's a couple motivations. I'm going to talk about ideas about phenomenology in a moment. But the number one motivation is certainly this idea of actionability, right? To be able to have models that give us the opportunity, the ability to take action. And in order to take action, I think ideally we know exactly what is happening and when it's happening. And so, again, this would be locating specific moments of time in specific persons, and those moments of time are rich with contextual information. Okay, so I mentioned linear models, right? So I think, I don't know what the real percentage is, but some overwhelming percentage of work in our field is is based on linear models, from the regression family, the general linear model. I think this has a kind of a default status in our field, and this is this approach that requires us to average across those rows one way or the other, whether those rows are people or whether those rows are time points. This is a necessity in that approach. And I think that regression especially tends to be seen as kind of a neutral model, that this is a first step or an initial step or a way to at some basic level throw some information into a statistical model and get some information back about the nature of the world. But what we often don't talk about or acknowledge is that actually regression models make very particular assumptions, so they generate their estimates within those assumptions, and the inferences that we're going to draw are, of course, constrained by the assumptions of a regression model. And there's several assumptions. Linearity is one of them. But the one that I want to focus on particularly is statistical control. which may seem like a strange thing to single out. But when we estimate linear models, there's this bit of math at the heart of it. And you can see here, I've noted, it's the ordinary least squares estimator in ordinary least squares regression. Um, but there are comparable approaches in maximum likelihood estimation. And either way, what it is this, you see the power of -1. When you take the inverse of that x prime x matrix, I won't go into detail here, but there's a few steps there, and there's some math that basically identifies the amount of linear dependence between the variables in the model, and then removes that, right? So this is this idea of identifying the unique contribution of each coefficient to the model, right? So we don't want to, when variables A and B overlap, we don't want to double count the B part of A and the A part of B, right? So this is a sensible thing to do, but it has consequences, and I want to talk about those a little bit. And I also want to emphasize that, I've said regression a few times, but this is true for all of these different models, this whole family of models. So structural equation models and multi-level models, kind of fancy new versions of regression like lasso and elastic net. So they're all going to generate estimates under the same assumptions. And again, our inferences are going to be constrained in the exact same manner. So for me, what this all comes down to is a word that's only recently come into my vocabulary, but the idea has been in my head for years and years and years. In fact, this is kind of the core, the central idea that motivated me to pursue idiographic research in the first place. And this is this concept of the estimand, right? So the estimates are the things that our statistical models produce. The estimand is what we want to know. And so the question is, are we choosing models that produce estimates that map on to our estimands? And there are times, lots of times, when of course that works fine. So just as the bullet point here says, like regression models are great. They're fantastic. I use them all the time. They're especially good, for instance, in work that I do for prediction. So we use elastic net, for instance, a lot. I like elastic net because it will allow you to offer the model many variables, many potential predictors. Some of them will be penalized down to zero. You can eliminate them, and you can kind of, in a fairly efficient way, locate different models for different people in an idiographic manner and make nice predictions. And we've done that with emotions. We've done that with smoking. We've done that with drinking, and we've done that actually with binge eating as well. And there's a nice paper out of my lab from Nicholas Leenertz in Psych Medicine where we looked at binge drinking and binge eating all in one paper. And again, we use Elastic Net and it works really nicely. There are also times, of course, when the thing that I'm kind of nitpicking here and getting hung up on, well, there are times when that's exactly what you're looking for. So we often have variable A and we have variable B, and we know that these are conflated or confounded or overlapping in some way. And the exact thing we want is to understand the unique contribution of A when we've removed the overlap with B, when we've partialed out that contribution of B. So, again, like linear models, regression models, they're fantastic when they map on to the things that we want to know. But there are times, and the first two bullets here are basically the same thing, just whether it's ordered or not ordered. There are times when we have A and we don't want to lose any of A. And say, okay, this is how much A contributes to my outcome. And now I want to see how much incremental additional information I gain from B. Now that, in fairness, will be reflected in your R squared. It's not that you don't have some approximation of that in a linear model. But again, this idea of estimates and estimands, when we're looking at the model, when we're trying to interpret the model, when we're trying to use the model to reflect an understanding of what's going on in the world, the things that we're measuring, we can't get that kind of incremental additive effect. The model is going to carve out the B from A and the A from B, and also there's no way to do it in an ordered manner, right? A and then B and then C. related, but also a separate topic. And the one that I'm most focused on actually today is this idea of phenomenology. So when we want a statistical model to give us some sort of insight into um, how the world functions and what it looks like, and how these variables kind of act together in concert as an ensemble. And for me, again, I'm an idiographic researcher. The examples that always come to my mind are idiographic examples. So, for instance, right, we might have a depressed individual, and we're interested in understanding what leads to their emotional distress. And so we're building a model, and we first look at loneliness, and we find, oh, wow, there's this really nice, strong relationship between loneliness and emotional distress. Let's say it's 0.47. But then we put in some symptoms of depression, depressed mood, anhedonia. We put those into the model, and now all of a sudden the loneliness coefficient drops down to 0.04, something like that. So it's non-significant, it's barely above zero, and we're going to make the conclusion that loneliness is secondary to or fully subsumed by, mediated by, depending on how we want to frame it. But we're going to assume that loneliness is really not an important factor for this person's emotional distress, that it's secondary to their depressed mood and anhedonia. And statistically speaking, that's true, right? In terms of the linear dependence, the covariance between those variables, it's not that that's incorrect. But again, I return to this idea of phenomenology. That individual isn't sitting there thinking, well, I'm not really bothered by my loneliness because I'm totally aware that, it's linearly dependent on my depressed mood and, no, right? So for that person, their loneliness, the reason you have that zero order correlation is because it is associated with their distress. And most likely they find that loneliness distressing. So how can we account for the way that that sits alongside their depressed mood and their anhedonia in a way that somehow more closely reflects how that person is experiencing it? So I have some thoughts about that. Obviously, I wouldn't be setting that up as an idea if I didn't have some responses to offer. So I'll show some examples of some data I've been collecting, looking at different contexts and emotional distress as an outcome. All right, so I need to set up a few things in order for all of this to make sense. And first and foremost, I need to talk about set theory because I'm going to be getting away from linear models. So I'm not going to be thinking about combining information, say, through linear combination, the way you would do in a regression model or SEM or multi-level modeling. Nor do I want to combine information, aggregate information together in something like a latent factor, like we would in factor analysis. So I need something to replace those. So I'm going to talk about sets. And I want to talk about sets in a very simple way. They're just collections of objects. They're going to comprise conditions that are present or absent, right? It really is this simple. Here's a set of one. We say this set has a cardinality of one, and the set reflects weather conditions and simply that it's cloudy. Here's a set of two that reflects that it's cloudy and raining, and a set of three that reflects that it's cloudy and it's raining and there's lightning, right? So it really is that simple. Equally simple is how we're going to get this into our data sets. So um, these are all dichotomous variables. Everything I'm going to show you today are dichotomous variables. And we want to think about the concurrent presence of whatever conditions we're interested in for a given set. So here the example is we want set ABC. So set ABC is only going to get a 1 when A is present and B is present and C is present. And in any other combination of circumstances or conditions, it won't get a 1, it gets a 0, right? So if we're in R, we'll use an if-else rule. If A equals 1 and B equals 1 and C equals 1, then 1, otherwise 0. And as simple as this is, again, it's a pretty simple concept and it's a pretty simple, the manner of statistical encoding, what we do with the data and how we get it into the data set is pretty darn simple. And yet, as simple as it is, I want to propose that this is an alternative. It's an alternative approach to aggregating information, to combining information alternative to, as I said, linear combination and the way we use a set of predictors to make a prediction or look at the multiple correlation with an outcome. And in that regard, right, the set contains the predictive elements. So A and B and C, they make some prediction about the outcome. And or I think sets can also be a replacement for the way we aggregate information in latent factors. So in that regard, the elements of the set are like the indicators of the latent factor. These elements are the ingredients of some construct. I'll show you some examples of another thing that we can use sets to replace, and that's lagged models. So something that has, been a bit of a frustration for me in over the past few years is wanting to think about sequential events, right? So A to B to C to D, that this happens and then this happens and then this happens and then there's some sort of outcome. There's a few problems you run into there. So one that I've written about, Aidan Wright and Johannes Zimmerman have written about, probably others that aren't coming to mind in this moment, is the idea of the scaling of our lags, right? So there's a question about whether we know the temporality of kind of anything we work with in psychology, and whether or not we know that appropriate temporality. Are we approximating that with our with the space and time between our pings when we're doing something like EMA? Because when you do a lagged analysis, right, you're stuck with that time scale. So if you measured things every 2 hours, then those lags are, changes between X and Y, over a 2 hour period. But what if something happens in seconds or if it happens in minutes? Or what if you have mixed time scales? So that can get pretty problematic. Not only that, we don't tend to look past a single lag. For instance, the most common approach to lagged analysis, I would say these days, is network analysis. And when people do temporal networks or directed networks, those are synonymous terms. Well, that's based on a vector autoregression with one lag, a var1. Um, so yeah, even though when you look at that network image, there's this sense, that A leads to B, leads to C, leads to D, but that's not true actually, because it's a var model where the A to B path is estimated concurrently with the B to C path, which is estimated concurrently with the C to D path. We actually do not know, we cannot know whether A goes to B, goes to C, goes to D. Okay, so I'll show you how we can use sets paired with uh, um, a certain approach to collecting our data through EMA, what I call a structured EMA, and we can get at sequences of 2 or 3 or 4. I'll show you a couple examples of 4, in fact. So yeah, so I think sets are pretty handy. I'm here to proselytize about them as something we can use in our science. And I think that they can be, not a replacement, but an alternative to using linear combination, to using latent factors, and to using lagged analysis. And then we don't have to deal with any factor loadings. We don't have to deal with any weights or coefficients. We're not making any assumptions about the interrelationships of the elements in the set. We're simply encoding the presence or absence of certain conditions. Now, of course, it requires the data to be categorical, and I understand people have concerns about that. And so that might seem like a strong assumption or a strong requirement, and I'll touch on that at the end. All right, so we've set up now, no pun intended. We've set up kind of what's going to be the container of our information in this framework we're going to talk about here. So now we have to think about, well, what's the analysis look like, and what's the context of the analysis? So that's this next step here. I like to think about these things in terms of sufficient conditions, and can I find the elements, the conditions inside of a set that are sufficient for some outcome to occur? Traditionally, this is a deterministic idea, so you might see something written like this, where when the set of sufficient conditions occur, the outcome always occurs. And we can think about this in terms of conditional probability, right? So the probability that y equals 1 given the set of conditions, if that's 1, that means that every time those conditions are present, then the outcome occurs, and so then we'll say the set is sufficient. So for instance, When it's just cloudy and raining, we might say the probability that there's lightning is 50-50. But when there's clouds and rain and thunder, where there's thunder, there's lightning, we might say. And so the conditional probability is 1, and those are sufficient conditions for lightning. We can also set a probability threshold, um, admittedly arbitrarily, that's somewhere below 1.0. And this makes a lot of sense in our field where we're used to dealing with uncertainty, we're used to dealing with some level of imprecision, and we're expecting some set of conditions to always predict an outcome might be unreasonable, right? But as I'll note here, and I'll touch on it again at the end, um, there aren't standards there, and we have to kind of work through what a good probability threshold is and how much uncertainty we think is acceptable. Okay, so assuming you're following along and you're bought in enough to keep watching here, uh, one thing that you get out of this approach, so you're building sets of conditions, you're looking at conditional probabilities, you're trying to see which sets of conditions are going to lead to the outcome you're looking at. Well, what you'll find is that there are times when you can find a really strong conditional probability, let's just say a conditional probability of 1.0, but it covers a very small subset of the total space of your outcome, right? So let's say you have a cause. Let's say you have a set of conditions and they're truly causal. And I'm going to keep it abstract here so I don't have to defend that with any kind of causal inference. Let's just say we have a cause. But that cause is infrequent. And it's actually one of several potential causes of the outcome. So the outcome occurs 200 times in your data set, but your cause only happens 20 times. So it only happens 10% of the time. Um, okay, well, if you look at that as a predictor in something, in some sort of statistical model, and you look at something like an AUC or an R squared, a pseudo R squared, you're going to get a bad result. Your evaluation is going to lead you to conclude that you probably should discard that predictor or that set of predictors. But again, you have a cause. It's a cause. And I think, we're a field in need of causes and we shouldn't be throwing them out. So I want to give us a framework to kind of think about this and think about why that isn't such a bad thing that you would get for instance, a poor AUC. Okay, so this is this idea from Mackey, 1965, and what he called Inus conditions, and these are insufficient but necessary parts of an unnecessary but sufficient condition. So the set of elements are sufficient. When they occur, the outcome occurs. Let's say it always occurs. But that set is unnecessary because it is not the only set of sufficient conditions. Now, the elements in that set are each necessary. You need those to be present to complete that set of sufficient conditions. But each one of them themselves, again, is insufficient. They don't cause the outcome on their own. You need to aggregate them together in a set of sufficient conditions together, and then that will cause the outcome. But it is one of multiple causes. So again, it's sufficient but unnecessary. So there's a lot of words here, but if I may, they're all necessary words to make the point. And the point being that outcomes can be multiply determined. And so if you have multiple causes, you're going to have multiple sets of sufficient conditions. And some of these sets of sufficient conditions might be highly specific but insensitive, right? So that they're infrequent, but when they occur, they cause the outcome. So again, you're going to get by the kind of traditional metrics that we tend to use. You're going to get an answer that would lead you to want to discard or disregard this set of predictors, potentially discarding a cause. Okay, so the classic example from Mackey for these Inus conditions is a short circuit near flammable material, and that'll be sufficient to cause a house fire. So that's how we'd write that as a set. But of course, other sets can be causal, right? A candle that's left burning near flammable material, an arsonist who brings gasoline to your house and lights a match and sets your house on fire. So there's all sorts of potential causes of house fires. And I think the candle one's a really good one to, put the spotlight on for a second because many people don't use candles at all in this day and age. Some people might use candles for ambiance or in some sort of special occasion, but we wouldn't disregard the wisdom that one shouldn't leave candles burning and one especially shouldn't leave candles burning near flammable materials. We wouldn't disregard that just because it's an infrequent cause of house fires, right? So it is a sensible idea that candles can cause your house to light on fire. And so we have a sensible response to not leave candles burning near things, even though, say, the AUC as a prediction, as a um, evaluation of the predictive efficacy of candles is probably going to be pretty poor in the modern world. Okay, so I'm going to walk you through some work that I'm doing in my lab right now, and that work involves building sets through algorithmic means, an automated approach to building sets, and I will show you that algorithm and describe it, and then kind of sorting those to find the sufficient conditions. And we have functions for doing this in this package. You can scan the QR code and it will take you to this page. We actually will be renaming this package because there's already a package named MI tools we just discovered, and that's for multiple imputation. Here, MI stands for mutual information. So that's the first algorithm that I'll describe. So what we do is we're going to use mutual information to evaluate the concurrence of these categorical variables. Everything I'm going to show you today is dichotomous, but this works with more than two categories if you want, but we'll just stick with the simplest case today. Why mutual information? Why not like a Pearson's correlation? Well, Pearson's correlation famously is great for linear relationships, not so great for nonlinear relationships. Mutual information is fantastic for both. So mutual information will pick up linear and nonlinear associations. So what you're going to do is you're going to offer some set of data, some set of variables to the algorithm, and it will pass through those variables and look for any potential pairs. A pair is established at a certain level of mutual information. Mutual information can be converted to something called a G statistic, which is chi-square distributed and therefore allows you to estimate a p-value. So in the algorithm, you can set a p-value at which it will accept or reject pairings. Everything I'll show you today was made with p set to 0.01, but you can do it 0.10, 0.05, 0.001, right? Whatever you prefer. So if the algorithm locates a pair, let's say A and B pair together, then what it's going to do is it's going to recode the concurrent presence of A and B as a new dichotomous variable, AB, right? So if A equals 1 and B equals 1, then AB gets a 1 and all else get 0. Now it's going to take those pairs, which again have been recoded into dichotomous variables. It's going to take these new paired dichotomies, pass those back through and see if they pair with any of the original singles to create triples, and so on and so forth. And so the algorithm will keep on building sets out until either it reaches a maximum level of complexity, so you can state how large you want the sets to be able to be. Maybe you don't want sets to get larger than 4 or 5 elements, or it'll stop when there's no longer significance. And of course, the larger your sets get, the lower the likelihood that you have that many elements concurrent. So it effectively gets harder and harder to find a significant p-value the larger your sets get. So now you're going to have a bunch of information. You're going to have all your original singles, all the variables that you entered into the algorithm in the first place, and now all these new doubles and triples and quadruples and so forth. So how do we sort this out and how do we find the sufficient sets? We have another algorithm that will perform a k-fold cross-validated estimation of the marginal probability of the target outcome. So that's the base rate of your target. Your marginal probability of all the different predictor sets and original variables. And then the conditional probability for the target given each potential predictor set or predictor variable. The algorithm also estimates marginal and conditional entropies but I won't talk about that at all, but I'll just acknowledge that those are there. And then finally, you're going to get an odds ratio. For every conditional probability, get an odds ratio, Fisher's exact test, and a p-value. So a little update. So something that I didn't share at APS, and in fact, as a function of seeing some other talks and having some conversation in the Q&A after giving this talk at APS, we've decided we're going to add permutation testing to this output. So very soon, this algorithm will give you the option to ask for a Fisher's exact test or a permutation test to evaluate the significance of your conditional probabilities. And then the estimates are concatenated, and you can search them and sort them in whatever ways you want to find the answers you're looking for. Okay, so let's talk about the data we're going to be looking at. This is an ongoing study in our lab. We have 62 completers as of right now, although I think I have some numbers later that are a little lower than that, but it's 62 folks who have finished up so far. These are community participants from the San Francisco Bay Area. They're recruited based on their experiences of anger, fear and anxiety, and emotional reactivity. So these are folks who are having a lot of kind of high arousal emotional experiences. They come into the lab for a baseline visit. They do a stress induction. We measure some physiology. I'm not going to talk about that at all. But what I do want to talk about is the fact that we do, so they're there for 90 minutes. The stress stuff is about 30. So we have an hour to do this really nice detailed training session with them. And we train them on the EMA itself. We train them on the language that's in the EMA so that they understand what some of the stuff means. And I'll walk you through that in just a second. So when I say structured EMA, there's a few things that means. And it's going to set us up for our analysis. So first of all, the folks get 8 pings per day, and these are on the hour. So I know a lot of us tend to use like pseudo randomization, so we try to avoid that idea that people know the pings are coming. But in this study, we want folks to know the pings are coming because we want them to be kind of doing a really nice detailed job of tracking their experiences. And we ask them at each ping to retrospect back across the last hour. And this is really key for answering some of the questions that I'll show you in just a moment. And again, so there's a training here. We talk about the role of the participants as citizen scientists, and that the quality of our science is directly a function of the quality of the data they give us and the job that they do filling out the surveys. Okay, so mostly yes, no items. I'll show you that in a second. There's some logical branching, some sequential ordering. I will also show you that. And just to kind of reiterate this point one last time, again, we talk through with the folks, like we show them, we have these nice videos that my research assistant Peter Baxter made. And so we show people, look, if you answer this way, the survey will look like this. If you answer this way, the survey will look like this. And we're upfront, like, you can do this faster, right? But please don't. We need you to answer honestly. We need you to answer earnestly, truthfully, accurately, all these things. And that will make our data better. And to my knowledge, this is the first study that's been set up to kind of do this specific thing. Okay, so here is the survey, and the first question is whether they've had a negative emotion or not. And this is key, right? Because if they say they have not, they skip this whole page you're looking at, right? And they come to this second page of questions. So it really trims the study quite a bit. But this first prompt, right? Have you felt? And this is a checklist, so they can check one or more. They can check as many of these as are relevant. And now we get down, and this is a kind of a, for lack of a better word, a special set of items, and they'll be relevant to later parts of the talk in some slides I'll show you later. This sequence that they get right through here. And we emphasize that this is sequential, right? And so the first question is, did you feel an urge to express or act on your emotions? And then if it was yes, they have an opportunity to give a continuous rating, a 0 to 100 slider. They can rate the degree of urgency. Did you express or act on the emotion? Were you interested in trying to regulate or change your emotion? Did you feel or believe that you could potentially regulate your emotion? Did you try to regulate your emotion? And then if they say yes, again, they get another checklist. And once again, just to reiterate, we've trained them on these terms so they understand what reappraisal, acceptance, problem solving, suppression, distraction, et cetera. They understand what these things mean. So then, was your attempt to regulate successful, and which emotion or emotions did you regulate? Then we have some contextual information, experiential avoidance, behavioral avoidance. Did you feel compelled to satisfy a need or an urge? Food, caffeine, alcohol, nicotine, sex, drugs. Did you satisfy, address, or reduce the need? Was it related to or result of the emotion you experienced? Positive emotion, conflict, support, feeling unaccepted. So I want to bring our attention down to the last question, which first of all has a trichotomous instead of dichotomous uh, answer format. That's just to kind of hedge our bets and make sure we're really sensitive to picking up our target. And then the question is, are you currently distressed? Right? So again, in the training, we emphasize this, and the phrasing of the survey is hopefully a strong reminder that everything other than this last question is retrospective. So we want them on the hour to retrospect about the last hour. And then for the final question, are you now in this moment currently distressed? So that gives us this temporal displacement, which admittedly is not going to be consistent in terms of the emotional and the emotion regulatory experience and the current distress. It could be as long as about an hour if they had had an emotional experience right after the last ping. And then it could be short as, just a couple minutes if the emotion had just happened. So, just to acknowledge that. All right, so here's some data. Here's a participant from the study. What you're looking at is an icing model. So this is a network model for dichotomous data. It comes from the Icing Fit package from Claudia Van Borkelu and Sasha Epscam. The icing model is ostensibly a contemporaneous model, but again, because we have that nice sequential ordering, we have this structured EMA, we actually know that there is a temporality, and these are two sequential paths to distress. And of course, because we don't see a connection here, and we know that rating urgency precedes intention to regulate, we know that there's this nice kind of mechanistic inference from this model we're looking at that's contingent on whether the emotion was or was not urgent. So if the emotion was deemed urgent, then they were likely to act on the emotion, likely to believe that they could regulate their emotion, but then likely to end up distressed nevertheless. Whereas if the emotion was not urgent, they were able to intend to regulate, attempt to regulate, be successful in regulating, and obviate distress. But what this model doesn't tell us, right, is the exact probabilities here. And there's a couple of reasons for it. It's not just that, well, the edges are colored lines and not numbers. It's that, well, these edges are estimated. There's two sources of attenuation. So the icing model is based on logistic regression. So we have that statistical control that's in place here. And then, of course, on top of that, there's some penalization as well. So I want to think about how to look at this kind of information with a little more precision in terms of the exact likelihoods, the exact probabilities, and then also, not having any influence of statistical control, no suppression or attenuation or mediation. I want to be able to lay these different variables side by side with each other and have a direct comparison of their relative contributions. Okay, so here's a visualization that I have created for this function. It looks like a network model. It uses iGraph, but it is not a network model. What you have is in the middle, here's your target. So this is distress. And at the bottom is its marginal probability. So for this individual, they were distressed 35% of the time. And then on the outside, you have your sets, right? So here is a set of the emotion was upsetting and the emotion was urgent, and that happened 18% of the time. And when it happened, there's your conditional probability. The individual was always distressed. You can also see that these are overlapping. We've got a lot of redundant information. So that the emotion was upsetting, that you acted on the emotion, for instance, that you intended to regulate or tried to regulate. Several of these set elements, these conditions are present uh, in all of these sets. So how do we work with that? How do we figure out how much it's contributing to explaining the outcome? Well, we very conveniently use something called the union, right? Because what we want is we want to be able to count 1, 2, 3, 4, 5, 6, 7, 8, 9 without triple counting 5 and 7 or double counting 8, 9, or 2, right? And that's the idea of statistical control. So we can contrast the union to something called the symmetric difference, right? And the symmetric difference is, if you can imagine a Venn diagram in your mind, or just let's just look at X and Y and try to ignore Z for a second, right? So the symmetric difference is we're going to take out this 2, 5, 7, and these crescent moons that are left, that's the symmetric difference. And that's, analogously, not exactly, but that's what statistical control is giving us. But then we're losing 2, 5, and 7, right? So what we want is, and what we get out of the union is, we want to be able to account for all numbers 1 through 9, again, without double counting 2, 8, and 9, and without triple counting 5 and 7. And so this in R, this is just as simple as OR coding. If X equals 1, or Y equals 1, or Z equals 1, then we give a 1, otherwise a 0. And there are these two ways to write this in set notation if you're curious. So now, understanding that, here we can look at another set of sets from the same individual we were looking at before. These now are kind of interpersonally related sets, so experiencing conflict, feeling unaccepted, emotions upsetting, trying to regulate. So again, we have a bunch of overlapping information, and when we take the union, we find that these sets account for 84% of the distress events, which is an intuitive number to me. I like this approach because probability is intuitive to me, but perhaps you're still used to linear models, so we can run this as a logistic regression. We get a pseudo R squared of 0.72, right? So pretty good. So now, here's what I was talking about with sequences and being able to avoid lag models. Now, again, it's pretty vital to the example I'm about to show that the EMA survey was set up the way it was. I got a question after this talk at APS. Wait, is the reason that you know that these are a sequence purely based on the phrasing of the EMA? And the answer is roughly yes. It's not just the phrasing, it's also the instructions we give to the participants and the understanding that these are sequentially ordered events. But yes, the temporality comes from the survey. And so let's contrast these two. We've got emotion was upsetting, intended to regulate, tried to regulate, and then what did they do to try to regulate? They attempted problem solving. And we'll contrast that against the emotion being urgent, intending, trying, and attempting problem solving. So when the emotion was urgent, that happened 4% less frequently than the emotion being upsetting, but then they were 10% more likely, 0.81 to 0.71, to be distressed. So consistent with participant 27, we have this kind of mechanistic functional role of urgency. But again, we've got this A to B to C to D sequential ordering in both of these sets, and we don't have to lag our data at all. So we don't have to deal with the messiness of setting up what would be a lag 3 and exacerbating our missing data issues and all those kinds of things. And this is accounting for 92% of the distress events, but it's important to emphasize none of these are conditional probabilities of 1. So that's a bit misleading because there's some imprecision in these. There are times, for instance, when these sets are present and the individual is not distressed. So that's something to think about. So this is a slide I just want to show kind of quickly because I want to use it as a contrast to a later slide. We have these two sets at the bottom here, involving, having a negative emotion that emotion being deemed to be upsetting and then avoiding feelings, and then same set of elements here and then avoiding thoughts. So when this person avoided thoughts or feelings, they were distressed 90% of the time. So attempting experiential avoidance and that experiential avoidance not being successful. All right, so we've been talking about sufficient conditions, and what I've found is the idea of necessary conditions, like, not necessary in an I-ness sense, like necessary to the sufficient set, because then really anything in the set you could think of as necessary, but just an idea of, again, something generalizable about the person, or perhaps if you're zooming out across a large data set about persons in general, can we think of conditions that in some kind of abstract sense or absolute sense are necessary? And I find that to be a little bit tricky. So I've been thinking about that in terms of um, the conditions that are required for any sufficient set, right? So if you have an element that is in all of your sufficient sets, then that element we can think of perhaps as necessary for sufficiency in general. Um, so let's look at an example of that. This is also a nice example as a point of contrast with linear modeling. So let's look at this. So we've got this set here that this individual was frustrated, and then they uh, rated that frustration, they deemed that frustration, their emotion to be upsetting. And that happened 29% of the time. So frustration and emotion was upsetting is actually present in all of these other sets. And then, of course, this happens more frequently than all the other sets. So that frustration, emotion was upsetting set subsumes all the other sets. And if you were to run this as a logistic regression, what you would get is all the variance goes to this coefficient and all of these other coefficients go to chance. So if we were running this in logistic regression, we would reasonably and rightly drop all the other variables. And we say, oh, well, this is quite efficient. We've got this really potent predictor that accounts for all the other predictors. It mediates all the other predictors. Um, but again, there's this idea of phenomenology that I want to emphasize, because something that's really interesting is by not dropping all these other variables and by keeping them here and looking them over, we can see, well, this individual they had emotionally upsetting frustration when they were alone. They had emotionally upsetting frustration when they were with others and experienced conflict with others. Right. So again, we get this insight into the phenomenology of the individual, that frustration that is above some threshold to be upsetting for this individual happens for them when they're on their own, happens for them when they're with other people and they get into arguments. And these are insights that we would not have gained had we dropped these variables because of the way logistic regression functions. Okay, so back to this idea of necessary conditions. Again, um, emotionally upsetting frustration is present in all of these sets, so we can probably conclude that frustration, at least frustration above the threshold where this person answered yes to the emotion being upsetting, that this is a necessary condition for this individual to be upset, and this accounts for 96% of their distress. So a little bit of a curveball, a little change of kind of approach here. I want to talk about this idea of coding mutually exclusive sets and the mechanistic specificity that it gives you. So remember I told you that there was that section of the survey that was kind of particularly important, and that was that the emotion was deemed urgent, that they had felt an urgent need to express or act on the emotion, whether they did in fact express or act on the emotion, whether they intended to regulate, believed they could regulate, tried to regulate, and whether they were successful. So these 6 variables create 64 mutually exclusive sets of possible ones and zeros. So here we're not just accounting for concurrence. So the mutual information algorithm is only looking for concurrence. It's not looking for absence. It's not concerned with absence. So if we have a set that's A and B and C, D, E, F, G, H, I, J, K, those are all left to freely vary. They can be present, they can be absent. The set of A, B, C is not holding all the other possible elements to any account. But in this approach, we are being explicit, specific, exclusive, that each set here is a specific pattern of presence and absence. So you can see the first set, all elements are present. It's not on the screen because it doesn't fit, but the 64th set, all elements are absent. And then the other 62 are the other combinations between all present and all absent. So this is a cool approach, and it gives a really nice level of mechanistic specificity. I'm going to take advantage of that in the next slide. Something that I absolutely need to point out, though, is that you get a lot less signal. So, for instance, uh, for lack of a better term, I'm getting hits with my mutual information algorithm on most of the participants in my study. In fact, the only time I'm not is when the distress is very low, and I'll touch on that at the end of the talk. But this approach, there's a lot of folks where we're just not picking up any signal, and for this individual where we are picking up signal, again, 5% of the time, 1%, 1%, 2%, 2%. So with the specificity also comes, a much higher kind of bar to clear in terms of these sequences being present. So I'm just going to kind of lump those together, tuck them over here. So all of those had an urge and an intention, and they had conditional probabilities of one. So I'm going to stack them together. We don't have to use the union because they're mutually exclusive. We can just add them up so they occur 11% of the time. But then I want to look at this. I want to look at these two sets. And again, these are sequences that occurred. So 9% of the time, this individual had an urge to act on their emotion, acted on their emotion, intended to regulate, believed they could, tried to, but then did not succeed. And when that occurred, they were distressed 87% of the time. But then 11% of the time, they had an urge, they acted, they intended, they believed, they tried, and they succeeded. And then they were only distressed 44% of the time. Nearly half, just about half. Um, and I'm going to use the C word here. I think that this is evidence of a cause, right? Because not only are these two sets mutually exclusive to each other, they are mutually exclusive to all 62 other possible sequences that could have happened in these six events, right? Now, it is worth acknowledging that I don't know how sexy or interesting of a cause it is to succeed or not succeed at regulating your emotion and that leading to being distressed or not. I think that that's not quite tautological, but it's a bit on the nose. But I do think this is a pretty exciting proof of concept of how we can use these mutually exclusive codes to kind of isolate these potential sequences and that it can work very nicely. Just to acknowledge, of course, we can also flip this around. We can predict regulatory success. For this individual, there were a bunch of predictive sets. I've just broken them up into two groups to be a little bit easier to look at. We've got some of these mechanistically specific ones, and they occur actually with much higher frequencies, so that's nice. And then we get those made by the mutual information algorithm. And these are sensible, intended to regulate, tried to regulate, successfully regulated, right? So, okay, if you intend and try and succeed, it makes sense that you're going to not end up distressed. Also interesting over here that the individual was compelled to satisfy a need, and they satisfied that need. That happened 31% of the time, and then they were not distressed. 25% of the time, that need was specifically food. Now, this individual was not distressed 93% of the time, but nevertheless, these sets are accounting for 63% of that non-distress. Here's another example where we can contrast with a regression approach and again emphasize what we gain in terms of phenomenology. You'll notice that the emotion being deemed not upsetting again, is present in all of these sets and subsumes all those sets. Not only that, I think this is a case where we are looking at something that's fairly tautological, right? So the predictor is that the emotion wasn't upsetting and then I'm not distressed. Like, okay, this is not necessarily an interesting finding. So there's a few reasons why we might discard this as a finding. But to focus on the regression contrast, again, all of the variance is going to go to this predictor. And all of these others are going to go to chance because this is accounting for all the other predictors. But then we miss some pretty interesting stuff going on over here. Because 36% of the time, this individual claimed that their emotions weren't upsetting, but they also indicated that they were avoiding their feelings and thoughts. And so, to draw a contrast with one of the individuals we looked at earlier in this talk, here's someone who may be practicing, effective experiential avoidance. And therefore, we might question, is the emotion really not upsetting? And again, that would be somewhat tautological to predicting distress. Or is it that they are practicing effective experiential avoidance, and for that reason, they don't deem their emotion to be upsetting? And that, clinically speaking, would be interesting. And these sets account for 97% of the non-distress in this individual. Okay, so I've already kind of made the point about logistic regression a couple times, but I just want to focus in a little bit more. So, like, what's the problem here? And again, there isn't really a problem. I mean, I think that's an important thing to emphasize. Logistic regression is great. I use it all the time. It's really fantastic. Like I said, just to mention the same paper, we have a paper last year in Psych Medicine from Nicholas Leenertz predicting binge drinking episodes, binge eating episodes, doing so very nicely with elastic net, which is kind of an extension of logistic regression, and it's great. But for one last time, for the folks in the back, the issue here for me is one of phenomenology and the inferences that we draw from interpreting our coefficients, which, in fairness, I think some methodologists might be watching this right now and saying, well, you're not supposed to do that. You're not supposed to single out a specific coefficient and interpret it. But so many of us do it. Of course, like we all do it, right? And it's an inferential error, and yet we do it. So let's look at this. We've got these two sets, and they're almost identical. So emotion was urgent, acted on the emotion, tried to regulate. And here we have emotion was urgent, acted on the emotion, intended to regulate. Now, these both occur about the same amount of time, 75% of the time, 76. Oh, no, excuse me. Sorry. 13% of the time, 14% of the time, although the point remains, they occur about the same amount of time. And their conditional probabilities are roughly the same as well, conditional probabilities of 0.75 and 0.76. However, when we run this as a logistic regression, we get an interesting set of conclusions. We conclude that when the emotion was urgent and they acted on the emotion and they intended to regulate, they were never distressed. When in fact, no, when that sequence of events occurred, they were distressed 75% of the time. So what's going on? Well, what's going on is regression's functioning as it's supposed to, based on statistical control, because this coefficient is the estimate when this variable is at zero. So what that means are these are the occasions where the emotion was urgent, they acted on the emotion, they intended to regulate, but they did not try to regulate. So for participant 46, there's something very important in terms of their experience of distress. There's something very important about whether they did or did not try to regulate. Because if they simply intended but didn't try, they didn't end up distressed ever. And that's why we get this zero. So the model's not wrong, and the model's not incorrect, and the model's not bad. What the model is, though, is somewhat misleading if we're trying to understand the phenomenology of this individual. And if we want to be able to side by side intention and attempt, where really, in terms of the phenomenology, in terms of the behavioral occurrences, these were equivalent. But obviously, there were some number of occasions where they had an intention but didn't try. They didn't end up distressed in those occasions. And that's why we see that coefficient Of course, the coefficient itself is a logit, but we can convert it to a conditional probability, and we get a conditional probability of zero. And it's just a bit misleading, again, in terms of this idea of phenomenology. The model's still functioning as it's supposed to. And if we're trying to make predictions, I'm sure that these predictions are just as good as I don't know, that they're probably just fine, is all I'm trying to say. I'm not trying to knock regression off the shelf. I'm just trying to put some other options on the shelf alongside it. Okay. So I've been kind of cooking this stuff over the last 5 years, and I've certainly heard a lot of skepticism about this approach as I've been kind of working it out and putting it together. So let's talk through some of those skepticisms. Okay, categorical measurements lose information. So yes, this is true when you dichotomize a continuum, right? So if I'm going to take a continuum and just slice it arbitrarily, and of course a median is a common way of doing that, I run the risk of totally misrepresenting the distribution of that continuum and certainly losing information otherwise in terms of correlations and predictions. And it's not a good thing to do, but it's also not what we're doing here. What we're doing here is identifying the specific presence and absence of conditions and experiences. Now, it's a separate concern whether that can be done well. I'll get to that in just a moment. But assuming it is, we're not losing any information. Although some might say, well, what about degree? You're losing degree. You're just getting kind. No, I would offer that we get kind and degree. Not only that, we get degree in a qualitatively informative way. So I've already shown in this talk, for instance, I can have somebody tell me whether or not they've had a negative emotion, whether they deemed that emotion to be upsetting, whether that emotion felt uh, urgent enough to need to be expressed or acted on, whether they did express or act on it, whether they intended to regulate it, tried to regulate it, right? So we absolutely can get differences of degree. And I would even offer that this is what many of us are doing when we're filling out a survey or a questionnaire or BDI or something like that. And we're trying to think about the severity of our experiences, the degree of our experiences. Often we're looking at qualitative examples of, okay, so I was angry, did I raise my voice? I was anxious, but did I leave? Like these different qualitative aspects that inform answers on a 0 to 10 scale or a 0 to 100 slider or something like that. And here we are capturing that same information, but with a lot more specificity about qualitatively what it is. Okay, fine, but you'll never get the measurement right, right? This is this idea that measuring things as zeros and ones is inherently problematic. And I don't know. I just seem defensive anytime I deal with this because I just think that this is plausible. I think that this is perfectly doable. I think that the data we're already collecting kind of shows that it works very nicely. Not only that, I would say we have whole industries in our field dedicated to measurement, developing measures and measurement, evaluating measurement, critiquing and criticizing measurement. There's a lot of effort and time and energy that goes into ideas around measurement. And I think if a fraction of that went into dichotomous measurement, presence absent measurement, I think we could do a lot of great things. Okay, fine. All this works fine, and this is all great, but no one's going to do this because people don't work with categorical data. And I risk sounding smug or smarmy or something when I say, unexplored questions can't provide answers. We are a field in need of answers, and I think that we should explore as many different avenues and possibilities as we can. And that's just kind of what I would say to that. Of course, there are limitations. The one that has really bopped me over the head so far, again, these numbers aren't up to date. We have 62 completers at this point. And the percentage is just a touch lower. I think we're at 23% right now. But it goes without saying, there's a chunk of our participants who aren't exhibiting a lot of distress. Now, my conclusion is really that's more about our recruitment and our evaluation and assessment of potential participants. But the point is that, if you're setting up a whole methodology to predict a target, it kind of falls apart if you don't have the target, right? So the lesson that I'm learning midstream in this study is it is vital to match your population and that population's rate of experience of a given target with what the target variable is. And of course, categorical measurement does need further improvement. I wouldn't be so, um, I don't know, naive to think otherwise. And I think the point that I would emphasize particularly is the way in which, words are so vital to this process with the way we collect data. So really trying to understand and figure out and refine those operationalizations and the phrasing and using things like the training, like we're doing, but really fine tuning what we are asking of participants, what they understand of those requests, and then what they're able to provide. I think that triangulating those 3 points is vital to capturing the right presence and absence. I didn't talk a lot about our trichotomous measure, but measurement approach. But shout out to Zach Cohen. He and I, kind of came up with this as an idea. Also, Gal Lazarus, who helped me think through this for another study that we're running. And again, I did mention this before. It's really about kind of hedging your bets in terms of having the right level of sensitivity for your target, right? So we have, no to some degree and yes, certainly, right? And really what has come in handy is having that yes, certainly. So for most people, it's been 0 versus 1 or 2, right? Basically 1 and above versus 0. But we have a handful of folks who have so much distress that there's really no way to make predictions based on the ones, and you have to isolate the twos. So then it's 2 versus 0 and 1. And I think that there's plenty of work to do there, like really working that out and kind of how to do that best, and maybe trying to identify places where that leads to problems. So far for us, it feels like a solution and not a problem, but that doesn't mean there aren't problems lurking around some corner. And then I mentioned this when I talked about arbitrarily lowering the sufficiency threshold from 1.0 to say 0.90. We love to complain about p-values and p of 0.05 and things like this, but it is nice to at least to have industry standards. Like we have 0.05, 0.01, 0.001, and we've kind of built intuitions around that, and methodologists have helped us understand that, well, really, maybe you should look at 0.01 and lower because those between 0.05 and 0.01 are the least stable. And right, so we have some standards and some ability to operate within those standards. And it would be nice to have that in this approach as well. Okay, so linear models, they're neither generic nor neutral. They make very specific assumptions, and specifically around statistical control, those assumptions can really provide kind of misleading inferences about what's going on in the data and what's going on in the data as a function of what's going on for that individual. Yeah, these ideas of covariance, what exactly you're getting out of linear combination, trimming those unique contributions and then adding up the variables as a function of that. The way that we evaluate with R squared AUC, these things are, I think, a little more abstract, a little vague, a little fuzzier than we tend to really reckon with. And what I've been, kind of hungry for or kind of pursuing is something that feels a little more tactile, a little more tangible, face valid, if you will, straightforward. And I think sets provide that. They provide an alternative means either for aggregating through linear combination as a set of predictors, or through factor modeling as indicators for a construct. And it's an alternative means that is transparent, it's readily interpretable. We don't have to make any assumptions about the interrelationships among the elements in those sets. And to touch on that, that might seem unsatisfying to some people. And I think that that's understandable. I say, oh, there's no factor loadings, no regression coefficients. And, some people might say, yeah, but I want those things because they give me a sense of how these things are put together in some sort of mathematical or mechanistic sense. And what I think, so there's a couple things I think. I think it's a nice approach to simplify, step back and say, well, let's identify what the ingredients are first. And let's do that with some amount of replication and reliability. So let's find ABC as a set of predictors two, three, four times. And then we can turn to separately investigating, okay, when I have A, B, and C inside of a set, what is happening there? Is it additive? Is it interactive? Is it some nonlinear function? Is it maybe actually that A, B, and C comprise some sort of formal model based on differential equations? You know, all of these things are possible. And I think what's nice about this approach is not needing to worry about all of that and just saying that when A and B and C are present, they potentiate, they lead to, they are sufficient for the outcome we're interested in. And then we can later separately interrogate and investigate what exactly is going on among A, B, and C. And yeah, finally, assuming that we're satisfied with that sufficiency threshold, the sets are actionable. And I think that this is a really lovely piece to this approach, right? So if you hit that sufficiency threshold, then you can act. You can provide a classification or a diagnosis or an intervention or whatever that action might represent. And I think that that's something that's actually kind of missing from a lot of our statistical and methodological approaches, which again tend to be based on continuous data and covariances and don't lend themselves so well to saying this thing at this point in time, and that's when you should act. So thanks so much. Thank you to all the folks listed here who have been vital in helping me to conduct this research. And I really appreciate your time and attention. And I will awkwardly stop the recording. Thanks.